movie I can save online. So the last 3 lessons of this first part of the unit deals with what we call trends of properties in the periodic table. We've already been introduced to the periodic table through a guy by the name of Mendeleev, who put them all in order, right? And Mendeleev actually used the trends of the periodic table. He built the periodic table using their physical and chemical properties, their boiling point or their melting point, their reaction with hydrogen, how they behave when they're dissolved in water. And that's what allowed him to build the periodic table. We now know that the trends that he saw have everything to do with the atoms and their electrons and how hard they pull on their electrons. So we want to take the next 3 lessons and talk about how strong of a pull a nucleus has on its electrons, and then we can talk about the trends and how these things can be affected. We will not be looking at reactivity with hydrogen. We will not be looking at boiling point and melting point. But we will be looking at things that we've just been recently introduced to. Ionization energy, the amount of energy needed to pull an electron off. How does it change when we go from, say, sodium to magnesium to aluminum? And how does it change when we move down a group from lithium to sodium to potassium? All right? So we'll look at how the trends are for things like ionization energy. And another one we just learned today, electron affinity. We'll be talking about how the atomic size is related and ionic size. All right? We'll talk about characteristics such as metallic properties, which ones are more metallic and which ones are less. And all of these things can come from these properties. All right. So we're going to look at how strong of a hold atoms have on their electrons, because the strength of this hold determines everything. Chemistry is the science of how atoms hold on to, trade, or share electrons. And it's all dependent on how strong of a pull they have on their electrons. And you might be thinking, oh, Mr. Sanders, you're talking about atoms as if they're muscly guys and they got, strong arms and they're pulling on them. Well, no, I'm not. You can use the term strong to describe any force that's holding on to something. A strong guy has, the ability to apply a strong force. But in this case, we're talking about that force of attraction between the positive nucleus and the negative electron. Okay? All right. I'm going to introduce you for the rest of this class on 2 factors that are going to determine how strong a nucleus pulls on an electron. And these 2 factors will be used over and over again in the answering of the questions that I ask you. So when we talk about ionization energy or electron affinity or size, it doesn't matter what we're talking about. They will always involve the same possible of 2 explanations that I give you. And it has everything to do with how strong it pulls on the electrons. So first, before we can talk about the trends, I'm going to talk about what affects how strong a nucleus is pulling on its electrons. Because after that, all of the answers come from these things. Okay? Before I talk about the 2 factors, I need to give you a little review of a physics lesson that involves electrostatics, which involves the attraction between opposite charges. This slide summarizes the rules of electrostatic attraction or the electrostatic force. And you need to keep these rules in mind when using your logical minds to answer the questions. These rules you probably learnt in grade 9 when you did your electricity unit and you talked about electrostatics. Pith balls, ebonite rods, rabbit's fur, etc., etc. I'm hoping these rules are not new to you. Number one, opposite charges attract, like charges repel. Have I shattered your earth by giving you this information? No. Excellent. Good. When it comes to talking about atoms, we're talking about protons attracting electrons and electrons repelling other electrons. You might say, what about protons repelling other protons? We're not going to talk about two atoms coming together yet. We're just talking about a single atom, which means I'm going to have protons attracting the electrons in orbit, or I could have the electrons repelling other electrons in orbit. Right there. Second, when two charges are close, the force is strong, and when the two charges are far apart, the force is weak. You should know this from when you have played with magnets. You're all in grade 11 chemistry. You're here because science has intrigued you in some point in time, which means I guarantee all of you at some point in time has pulled off two refrigerator magnets and sat there and played with the magnets, right? Am I right? You did, didn't you? Go home and play with the refrigerator magnets. And I'm hoping that you've dealt with ones that are strong enough that when you pull them apart, you realize, let me bring them as close as together as I can without them touching. Yeah, that's one of the great games of magnets, right? And no matter how strong you are, when you get them close enough, they come together. Oh, jeepers, come together again. And that's because when the magnets are close, the force is great, and when the magnets are far apart, the force is weak. Nothing. There's nothing here. I can hardly feel anything. It actually drops off very quickly, right? It's actually an exponential decay if you're mathematically inclined, all right? It drops off very fast. No, sorry, it's an inverse square relationship. It's not exponential decay. You guys don't care because you don't know what an inverse square relationship is. Anyway, it doesn't matter. That's what it is. And what I'm trying to say is it goes from being very strong to being very weak, right? If you pull on a spring or an elastic band, that doesn't work like a magnet. A spring or an elastic band, the force actually grows when you pull it apart. That's not an inverse. It gets stronger. If you were to pull on something like silly putty, it actually works more like this. Has everybody played with silly putty before? You pull the silly putty apart, and you know how it kind of stretches, and then it just kind of goes, it just falls apart, right? A spring doesn't do that. It actually gets stronger. That's not the way this rule works. It's like silly putty. Oh, then it just falls to pieces. Magnetic force, when they're close, it's strong. When it's apart, yeah, it's nothing. Pulls apart like nothing. When electrons are close to the nucleus, yeah, it's going to take a lot of force to pull it off. But if an electron is far away from the nucleus, nothing. All right? So that's the way we're going to apply it. When the charge is big, if there's a lot of protons, the force is strong. In terms of a magnet, these magnets are getting pretty old. They're a little wimpy. But if I have a magnet like, where's my magnet? And I don't see it. Where's the blue magnet? Lost the blue magnet. Big blue magnet. What's that? Oh, yeah, those would work. Those are strong. Yeah, no, I'm not doing that. But yes, that's a great example. All right, I will. Stay. So, if I'm taking these two, right? Made the joke. Oh, a lot of work. Not, this guy. Actually, it's not that strong. It didn't work at all. This is strong because it's large, but this little guy isn't holding. I need a second large one, like I need that other big one. I'm not going to do that. Danger. Danger, danger. Actually, they'll break. These are ceramic magnets. Essentially, if I had a big magnet, stronger force. If I've got a nucleus with a lot of protons in it, then that's going to pull harder on the electron because there's a lot of positive charge there. Okay? All right. Now, those are the essential rules. Let's now apply them to our atoms. So this is now going to be the two factors that you're going to use to answer every one of the trends that we talk about from here on in except one. I'll tell you that except one. But every other one you do that. Here are the two factors. Number one is the orbit number, or how many orbits that atom has. Now my picture here is representing the valence electron of two different atoms. And what I'm doing here with this big red arrow is looking at the strength of the force on the valence electrons. Because remember, valence electrons are the ones that are going to bond, gain, lose. We only care about the valence electrons. Now, when we compare atoms, I am going to compare them either above and below each other in the same group, or left and right from each other in the same period. If I am comparing two atoms that are above and below each other, the main difference is they have more orbits. So if I'm comparing sodium to rubidium, I'm going to use this argument, because the main difference between sodium and rubidium is the fact that rubidium has 5 orbits and sodium has 3 orbits. So this is the argument I'm going to use. Again, in my picture, what I'm attempting to describe is how the strength of the pull on the valence electrons changes when we move to another orbit out. When you move down the periodic table, you have a greater number of orbits, and therefore there's a larger distance between the valence electrons and the nucleus. And when you've got two charges that are far apart, the electrostatic force is weak. You might say, but this has more protons, Mr. Sanders. But yesterday I described to you that when the orbits get big, they get big fast. And the fact that they get big really fast cancels out the extra protons. So it is actually easier to take an electron away from an atom that is lower in the periodic table, even though it has more protons. So it's easier to take away an electron in the outer orbit of cesium, out way off in the 6th orbit, than it is for hydrogen. Even though cesium has 55 protons, the extra distance of the 6th orbit makes that electron come off with no effort whatsoever. So as you move down the periodic table, there's a larger distance between the valence electrons and the nucleus. This results in a weaker electrostatic attraction between the electrons and the nucleus. It's easier to remove. Okay? So that's factor number one. And when we get talking about size and ionization energy and electron affinity, and we're going to explain all this stuff, you will use that logic when comparing two things that are above and below each other. And we'll practice a whole bunch of them. The second factor. The second factor deals with left and right on the table, which means they have the same number of orbits. So the orbit effect is out. the nuclear charge on the nucleus, or the number of protons. They mean the same thing. In my arguments, when I get to talking to you and explaining and helping you to understand and how to make a firm argument on why something is higher than the other thing, I tend to say number of protons. All right? Nuclear charge, people often confuse nuclear charge with electrostatic force. Nuclear charge is the charge on the nucleus, the number of protons. Electrostatic force is that pull between two opposite charges. This is the last slide for today, but I do have a little explanation I'd like to do before we start flipping books closed and all that type of stuff. And it won't be much. I'm just waiting for you to finish writing, and then I'm going to do a quick little explanation. I just stated that the greater the charge, the stronger the force. So in this case, what have I got? 12 magnesium versus 13 aluminum. One has 2 electrons in the outer orbit, the other has 3 electrons in the outer orbit. You might say to yourself, but they're both neutral, Mr. Sanders. Why would they pull any differently? Remember, they're neutral to an electron that's very far away from it. Deer in the headlights, right? But an electron that's in the orbit is so close that it's really not being affected by its neighbors, because these 3 will be spread over the orbit itself. So this electron in this orbit will feel the pull of 13 protons, which is greater than the electron in this orbit that feels only a pull of 12 protons, because they're spread over the orbit. They're not way out at a great distance. So even though they're both neutral, and even though one has an extra electron compared to the other, the individual electrons in the valence shell, the outer orbit, will feel a greater pull if there's more protons. The more protons with the same number of orbits, the greater the pull. The further to the right the atom is on the table, the greater number of protons it has for the same orbits. The larger number of protons means a stronger electrostatic attraction between the electrons and the nucleus. And aluminum is holding on to its outer electrons harder than a magnesium. Okay? Those are the 2 pieces of logic that you'll use over and over again to explain these trends that I will start to talk about tomorrow. All right, that's that.